Okay, this is June 2016, paper one, question number 9. The diagram shows an electric motor which has a commutator, the brush, and another brush. The electric motor needs a direct current. Explain what is meant by direct. Well, there's only two currents you need to know about, in fact, three. So we've got direct, which means in one direction. That's going directly in one direction only. So you could say the current passes or flows in only one direction. Alternating, where it seems to change direction or it does change direction. And then what is conventional current? So you need to know those three things. Explain the purpose of the brushes and the commutator in the DC motor. Okay, we need to explain this. So it provides a connection. So first of all, it provides a connection. What is a motor? Well, a motor it takes an electric current that's within a magnetic field and that causes a movement. So it provides a connection, but it also reverses the current in the coil. Right. Why does it do that? Well, it provides that connection to reverse the current because if there were just two wires that went into the coil and it was asked to spin round, well, now the current is flowing in the same direction around the wires, but it's flipped over. So that's going to cause it, if you think about the left-hand rule and the forces, that's going to cause it to flip back. If you need any more information on that, and there's some really good pictures and diagrams and videos, go and look at the lesson on Firefly. So it needs to do that. It reverses the current every half turn so that the force is always in the same direction. My writing isn't great, but look at the mark schemes. So it's always in the same direction. So if you want it to keep spinning in the same way, we have to keep flipping the direction of the current so the forces on each side of the wire keep it flowing around in the same direction. The motor turns clockwise when the direction of the current goes from positive to negative. State what happens to the motor when both the magnetic field and the current are reversed. If we reversed one, it would go in the other direction. So if we reverse two, it's like we're reversing the reverse. So it's going to keep going clockwise. No overall effect because of those two reverses. They cancel each other out. The photograph shows a machine at a coal mine. The machine lifts up a container of coal from the mine and lowers it empty containers down. The machine uses an electric motor connected to a 600 volt DC supply. The maximum current in the motor is 4,000 amps. Those are probably going to be very useful. State the equation linking current, power, current, and voltage. Power equals current times voltage. And what do you think they're going to do next? They're going to ask us to calculate something with that. They've just given us those two values, so it's going to be 4,000 times 600 volts. What do we get for that? You get, you actually get 2400000. The unit is going to be watts, but look what they've done. They want it in megawatts. So what do we have to do? Well, if that's a million, then we have to divide this by a million, which would leave 2.4 megawatts. The machine lifts a load weighing 400,000 newtons through 190 meters. State the relationship between work done, force, and distance moved. We're going to guess a lot of these are just take the three of them and multiply them. Equals force times distance. And again, what are they asking us to do? Okay, calculate the work done, which is going to be the force, 400,000 newtons times 190 meters, and that's going to be 76 million joules. And look, we can actually leave it like that because they do want it in joules. The machine uses an average or mean power of 1.9 million watts to do 67 million joules of work. Calculate the time needed to do this work. So they give these two values, watts and joules. So what do you think that we're going to need to do in order to calculate the time? Well, there must be a link between them, and it's power equals energy over time. So if you want the time, that equals energy over power, which equals that's 67 million joules divided by 1.9 million watts. We got 2 millions there, so we can cancel those out. So it's 67 divided by 1.9, which is 35 seconds. Remember that the time here, if this is in watts, which is joules per second, and this is in joules, the only unit that would leave us would be seconds. State the effect of using a lowered average power to do this work. Well, if this number was lower, it's going to take longer. So it's just a state, so it takes longer time. And that's question number 9.